Hello, I'm Paul Beckwith, and of course this is Shackleton the Great, Shackleton the Explorer. Had to coax him to help me out with this video with a little bit of cat food. It's dry food, of course. I'm not going to go anywhere near the wet stuff in terms of holding it with my hand. Anyway, most of you are probably aware of James Hansen, one of the top climate scientists who's been, active for trying to get the word out on climate change for many, many years. And he wrote a book, Storms of My Grandchildren. I just checked, it was written in 2010, published in 2010, so 10 years ago. And he was talking about how weather would go berserk because of abrupt climate change or rapid climate change. So I'm going to talk about some of the updated plots that he has on his website, and there's all kinds of different topics: the energy, global energy production, global temperature, temperature at the poles in the north, in Antarctica, the equator, sea surface temperatures, continental temperatures, distribution over time, etc. A little bit about solar, sunspots, solar output, effect on climate, greenhouse gases, of course, CO2, methane, CH4, nitrous oxide, N2O, the ENSO, the El Nino and La Nina conditions and where we're at with that, global precipitation, drought, winds, hurricanes, tornadoes, wildfires, sea level. Okay, I'll talk about plots of ice sheet loss, specifically Greenland and Antarctica, sea ice, bit about species, one of his pet things to look at is monarch butterflies, their migration patterns and their numbers over time. Forcings, aerosols both in the stratosphere and in the troposphere, air pollution, and a little bit on paleoclimate. So this is going to be a video or a few videos showing plots, showing loads and loads of plots, some of which you've probably seen, but others I'm sure that you haven't seen. So let's go to the beginning here. Of course, I spoke last about bizarre warm weather thunderstorms occurring in the high Arctic near the North Pole. Okay, the Arctic sea ice is dropping like a rock. So we'll see what happens. It'll be interesting because it was dropping extremely quickly last summer, and then it kind of just stopped melting out. The curve completely sloped up, surprising lots of people. So, we'll see what happens this year. I mean, if trends continue, of course, it's going to set new records. It's going to blow away the previous 2012 record. But, the sea ice has shown resilience that we've kind of not expected. So there's lots of feedback loops going on. And it's really hard to predict what's going to happen in 1 year. I still have to say that. So look at my website, paulbeckwith.net, if you're not familiar with it. Facebook and Twitter, and also my YouTube channel. You can just Google my name with YouTube to find my videos directly. I'll say a little bit about the coronavirus. We just passed 14 million cases worldwide. U.S. 3.6 million, Brazil just passed 2 million, India just passed 1 million, global deaths just passed 600,000, approaching 140,000 deaths in the U.S. The key thing is, this is an indoor disease. It's transmitted indoors. It's transmitted inside when there's lack of ventilation with the outdoors. So wearing masks is vital inside. Outside, transmission is very low. You don't need to wear a mask outside as long as you're social distancing. And you know, the best thing you could do as an individual is boost your immune system. I mean, one of the things, you know, we're searching for vaccines that may never materialize. The closest thing I can see to a vaccine is vitamin D. It's very interesting. There's some studies there's lots of studies on vitamin D, and there's lots of reason to believe that you know, people that have, you know, high levels of vitamin D in their body are somewhat less, they won't get as ill. Okay, so that's a, you know, I'll probably do some videos on that specifically, but anyway, stay safe out there. Okay, so if you Google updating the climate science, James Hansen, he's at Columbia University. It's the Climate Science Awareness and Solutions Organization, CSAS, and this is his sort of one of his main web pages, and there's an index of all kinds of different things that he's looking at. So let's look at some of the plots. So this is the United States energy consumption. You know, some of the projections from years ago were much higher than what we've been seeing, but this is the trajectory. So we've got coal, we've got oil, we've got gas, we've got nuclear, and then we have renewables, and the energy is in quadrillion BTUs per year, and it's been rising slowly. You know, some fluctuation, but it needs to be significantly cut. The fossil fuel burning things like coal, oil, and gas. Okay, this is emissions, global emissions in petagrams of carbon per year, and you can see that this is of petagrams of carbon. It's not of CO2. Be careful about petagrams of CO2, because in order to get the CO2 numbers, you need to multiply these numbers by the ratio of the molecular weight of CO2 to the molecular weight of carbon. Molecular weight of carbon is 12, oxygen is 16, so 2 oxygens is 32, plus the carbon is 44. You need to multiply these numbers by 44 over 12, which is 11 over 3, which is 3 2/3, or 3.667. Okay, so if you multiply this by 3.667, you get about 36.7 petagrams of CO2 per year, and that's a petagram is equivalent to a gigaton. You can do the conversion. So that's how much CO2 is being produced, emissions of CO2 per year. And if you look at the amount that stays in the air, the airborne fraction, this is the average, the blue line here. You know, it's somewhere between slightly over 40%, slightly under 60%. So about roughly 50% of the emissions stays in the atmosphere. Okay, and because it's climate change, the other 50% gets absorbed mostly in the oceans, also in the soils, etc. Now this is the annual CO2 growth rate. So it was, you know, on the level of 1 parts per million per year in the atmosphere, and it's been working its way up, and it's now over 2 parts per million per year. Some years are higher. We're reaching up to 3 in some years. Okay, so these growth rates are very, very high. This is the per capita or per person emissions, and this is carbon per year per person, the left scale. So U.S. about slightly over 4 tons of carbon per year per person. Canada and Australia are also high. Australia is slightly higher than Canada. You know, Russia's pretty high. And, you know, if you look, you know, China and India are much lower. They have much higher populations and so on. So you can compare them all. This is the 2018 per capita emissions. And this is cumulative emissions from 1751 to 2018, and you can see the U.S. Leads. The UK is up here, because these countries have been burning the stuff for much, much longer than other countries. And if you look at the breakdown, you can see how much is due to coal. You can see the breakdown to coal versus oil versus gas. This is cement production, produces lots of CO2. There's something from flaring here. This is the global emissions in gigatons of carbon per year. So again, we're getting up to 10. Remember, a gigaton of carbon per year is the same thing as a petagram of carbon per year. It's the same unit. It converts to the same thing. These are the annual emissions in 2018. This is a total global 10.2 gigatons of carbon per year. China's almost a third, 28.8%. U.S. 14%. India 7.3%. Then Russia, and so on. And you can see the breakdown here. And this is the cumulative emissions. So cumulative emissions, the USA is of course much, much higher. China's catching up. Europe and Eurasia is pretty high. Okay, so you can see the breakdown there. Lots of curves on that. Now, this is global temperature. Now, the base period is 1880 to 1920. Okay, so take the average between those years. That's the base, and you can see where we're heading here. There was a super El Nino here in 1996. There's a very powerful El Nino in 2015, 2016. These were called super El Ninos, cause lots of release from the ocean warming. So the warming's higher here. And if you do, so this is the 12-month running mean. It's the blue line. The data points, the means for each month are the black dots. And this is the best fit from 1970 to 2020. The green line, and that's a slope of 0.18 degrees Celsius per decade. So that's the sort of warming that we're looking at. And you could argue that in the last few years, say since 2010, the slope is higher. It's much higher. If you fit a linear curve to the last 10 years or so, you could. It remains to be seen if this is a new trend or if this is just noise. Okay, if we look at surface temperature relative to 1951, oh, by the way, in order to convert this mean to 1750, you need to add about 0.3 degrees. So we're already at 1.5 degrees by this reckoning. You have to be careful of these baseline shifts. I've talked about that quite a bit. This is surface. This is the spatial distribution on the planet. This is June 2020 relative to the 1951 to 1980 mean Junes. And you can see a lot, tremendous heating this year up in this region here over Siberia. This is April to June 2020, and this is over the last year, July 2019 to June 2020. You can see this area has the most warming out of all of the areas. A lot of warming overall in the Arctic, also some in Antarctica, but these regions here, this region has been persistently warm. This is okay. So this is this is relative to the 1951 to 1980 base period. So the baseline is just shifted here, and you can see the global surface temperature. So these are the records, the temperature anomaly, and you can see the record high before 2020 was in 2016, and here we have 2020. So in the 4th, 5th, and 6th months, we've set record highs. These are the El Nino temperature anomalies in the last number of years. So strong El Nino in 2015, 2016 caused that spike here. And this is the this is another view of this, the way to depict this same data. So strong El Ninos in 2015, 2016 caused this spike, but we're getting this without a strong El Nino now. So I'll continue. Thank you for listening. Please check out my website, paulbeckwith.net.